Welcome to this video on the topic of networks. In this video, we're going to have a look at how we can discover the shortest path between two nodes within a connected network. To do this, we're going to use an algorithm called Dijkstra's algorithm. But before we can look at Dijkstra's algorithm, we first have to look at some potentially new notation and terminology. If we turn our attention to the network shown over here, we have a network composed of 4 nodes and 3 edges. Now this network is arranged in a series fashion, as in all of the network or all of the nodes are chained one by one, so C, then A, then B, then D. Now some of the new items we see on here are these boxes, these purple numbers, and potentially these green numbers. Now starting off with these red boxes, what the boxes represent is whether we have visited the nodes or whether we have yet to visit the nodes. So in this case, we have visited nodes A and C, however we're yet to visit nodes B and D. The idea of visiting a node will make more sense when we get into the algorithm. Now the next thing we turn our attention to are these green numbers here, here, and here. What these green numbers represent is the weighting associated with the particular edge in this case, or an arc if we're working with arcs. The weighting itself simply means how much it costs to travel between nodes. So to travel between node A and C has a costing of 4. Now the final item we look at is this purple item seen here, here, and here, but not here. What this purple item represents is the path weighting. So how much it costs to reach a particular node from the starting node location. Now in the case of C, it costs a weighting of 4. To be able to reach C from A, and from B it costs a weighting of 7. It's simply a matter of adding the arc weights or the edge weights together. Now moreover, there are 2 types that we can get. The purple numbers that are inside the red box are finalized, as in that they cannot change, and the numbers that are outside the red box, we call them prospective, or I call them prospective, in that they're subject to change in the future. Alright. Now that we've got this terminology out of the way, let's have a look at the rules associated with Dijkstra's algorithm. So Dijkstra's algorithm is simply an algorithm that's going to reveal to us the shortest path within a connected network. Now looking at that, we have 7 rules. The first rule we start off with is we need to identify our starting node. From there, we assign the starting node a path weight of 0. If we look at the example network above here, the node A is going to be our starting node because you can see it's got a path weight equal to 0. Now the next step is we want to visit unvisited node with lowest path weight. So you're going to visit the node with the lowest path weight. At the start of the algorithm, you only have one node you can visit, which is the starting node, in which case it's A. To denote that you've visited the node, you're going to put a red box around it. Once the red box goes around it, finalize the path weight as well. Alright, next step is compute the prospective path weights to adjacent unvisited nodes. In the case of A, the unvisited nodes would be C and B. The prospective path weights being that you're calculating how much it costs to get from A to C, in which case it will be 0 plus 4, so the prospective would be 4, and 0 plus 7, so prospective is 7. After which, if new prospective path weights are lower than existing, replace, alright? And then if unvisited nodes exist, go to step 3. So because after visiting or after looking at node C and node B from node A, you're going to have C, B, and D, which would be unvisited. You prioritize the node with the lowest pathway, in which case it would be 4, and therefore you draw a box around 4 to visit it. You repeat the algorithm again until you no longer have any unvisited nodes within a network. Alright, so let's turn our attention to example A here. In example A, we have a network composed of 5 nodes and 2, 4, 6, 7 different edges. We want to find the shortest path from A to E. We're going to find this using Dijkstra's algorithm. Now Dijkstra's algorithm says that we need to identify first our starting node, in which case we're starting at A. As a result, we're going to assign a path weight of 0. Next step is we need to visit any unvisited node with the lowest path weight, in which case A is going to be the lowest one. The other paths, or the other nodes themselves, the path weights are unknown, so we don't even consider visiting them until we know a path weight for them. Alright, next step is we need to calculate the prospective path weights from our current node to our adjacent nodes that are unvisited, in which case we have B and we have D. The prospective path weight from A to B is going to be 0 plus 4, and the prospective path weight from A to D is going to be 0 plus 3. As a result, the cost of getting to B from A is going to be 4, and the cost of getting from A to D is going to be 3. Next step is we have to observe which nodes are unvisited and of which one has the lowest path weight. In our case it's D, so we're going to now visit D. From D, we have a look at our adjacent unvisited nodes. We have A, C, and E. However, we're not going to even consider going back to A because we've already been there. Rather, we're only looking at C and E. Prospective path weight to get to C is going to be 3 plus 1, and the prospective path weight to get to E is going to be 3 plus 7. So it's composed of the current path weight plus the weight associated with the edge over here. Calculating these, to get to C it costs 4, and to get to E it costs 10. Next step along, we're going to visit the node with the lowest path weight. Now in which case we have B and we have C. It doesn't matter which one you choose to go to because they're equal, but I'm going to prioritize B because it's been waiting in the queue longest. It's up to you which one you want to visit if they're the same. Now from B we're able to reach A, C and E. Now we're not going to go back to A because we've already been there, but we can have a look at how much it costs to get to C and E. Even though they've got a path weight assigned, we can see if we can get a cheaper path. Now to get from B to C it's going to cost 4 plus 2, and to get to E it's going to cost 4 plus 5. For C at least, it's not viable to travel to C from B because it costs 6, but to get to E it's cheaper, it costs only 9. So as a result, we'd scrap the 10 and go for the 9. Now next step is we move to the node with the next lowest path weight, in which case it's going to be C. C is now finalized. And we observe which nodes we can visit that are yet to be visited, in which case it's E. To get to E from C, it's going to have a costing of 4 plus 3, which is going to come out to be a value of 7. And thus, the cheapest way to get to E is via C. Now what we've got here are the calculations showing the cheapest route or the cheapest path through this particular network to go from A over to E. Writing this out, we go shortest path is going to be A, and then from A we went down to D. From D we went up to C, and from C we went across to E. And it had a costing or a path weight equal to 7 units. Alright, now this is example A. Now one of the problems that you might have noticed with this particular algorithm is if you have many nodes within the network itself, it's going to be very confusing when you get to the end of the calculations to know what the actual pathway was for the node or pathway was through the network to get from the start to finish. In the next example, I'm going to show you how you can symbolize or how you can record the path that you take for the entire network. But for this example here, for a small network, this is a viable way of doing it. Alright, going down to example B, we have slightly bigger network. So we've got 2, 4, 6, 8, 10, 12, 14, 15 unique nodes, and we have 2, 4, 6, or 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22 different edges we're going to travel across. So the complexity has been increased significantly. Irrespective, we're still going to find the shortest path between nodes A and O using Dijkstra's algorithm, but I'm going to make a slight modification to the notation just so we can see all of the pathways through the network that will lead us to O. Alright, step 1, we're going to identify our starting node, in which case we're starting at A. As a result, I'm going to assign A a pathway of 0. Next step is I'm going to visit my node with the shortest or lowest path weighting, in which case A is the only potential node. And then we're going to have a look at the adjacent nodes and calculate the prospective path weights, in which case we can go from A to B and A to F. Calculating this, it's going to be 0 plus 2 and 0 plus 1. Now here's where the new notation is going to slip into the mix. When I'm calculating these, the pathway to get from B via A is going to be 2, and then I'm going to throw a little subscripted A in there, and that's going to tell me where I came from. Similar with F. So make sure it's subscripted, not like that. Alright, now favoring the pathway, or favoring the node with the lowest pathway, we're going to go to F. And then we're going to calculate our prospective path weights from F to G and K because they're the adjacent nodes. So to get to G, it's going to cost 1 plus 2. And to get to K, it's going to be 1 plus 4. The prospective path weights are 3F and 5F. Moving across, we go to B as it's got the lowest path weight. So now we visit B. Then we can travel from B to C and B to G. To get to C, it's going to cost 2 plus 3. And to get to G, it's going to cost 2 plus 3 as well. Consequently, we're not going to visit G via B because it costs too much. We've got a cheaper route via F, but for C, that could potentially be a viable option because we've yet to find any other routes to that or any other pathways to C. So I'm going to go 5B. Moving along, next lowest path weighting is G. Looking at where we can get to from G, we can go to H, which is going to be 3 plus 3. And we're able to get to L, which is going to be 3 plus 5. Calculating these, we have 6G and we have 8G. Moving on, we pick the next lowest pathway. I'm going to pick K. We could have gone to C, but I picked K because it's been in line the longest. That's not a rule that you have to abide by in Dijkstra's algorithm. It's just something I like to do. You could go to C straight away if you wanted, and then go back to K. From K, you're going to go, the only potential node you can visit is G, and it's going to have a costing of 5 plus 2, which will be a value of 7, and thus we've found a cheaper way to get to L. So we get rid of that 8. Moving along, we have C. From C, we're able to visit both D and we're able to visit H. To get to D, it's going to have a path costing of 5 plus 5. And to get to H, it's going to cost 5 plus 6. Consequently, you would not visit H, or you would not visit H via C because it costs too much. However, you may visit D via C because it only costs 10C and it's the only way we can get there at this point in time. Next one along, we're going to go to H. From H, we are able to visit I at a costing of 6 plus 2, and we're able to visit M at a costing of 6 plus 1. Becomes 8H, 7H, and then we look for the next node along, in which case it's going to be L. From L, the only node we can visit is M, and there's no point even calculating that because they have the exact same weighting. So whatever we add to 7 is going to be greater than 7, so that's finalized. Next one is M. From M, the only node we may visit is going to be N, and it's going to come at a path weighting of 7 plus 4. This will result in a overall pathway of 11, and we came from N, M. Next one along we have I. From I, we are able to visit J, as well as D and N. Firstly, looking at D, we can go 8 plus 2. J, we can go 8 plus 1. And N, we can go 8 plus 2. As a result, to get to D, it's going to be a value of 10i, but we really don't care about that because we've already got a pathway that takes us to D. So you wouldn't worry about doing that path. To J, we haven't calculated any paths other than this one yet so far, so we'd say 9h. And from N, it's going to have a costing of 10. So we found a lower weighting to get to N. Next one along, we pick our J. From J, we are able to get to E at a costing of 9 plus 3. And we're able to get to O, and it's going to cost us 9 plus 4. Calculating E, it's going to be a value of 12. And calculating O, it's going to be a value of 13J. Should be uppercase. Picking or prioritizing the node with the next lowest weighting, we'll go to D. From D, we're able to get to J. However, we've already got can already get there for the same cost by going through J, so I'm not going to worry about that. Next along is going to be N. From N, we are able to travel to O. To get to O, it's going to cost 10 plus 2, and as a result, we have a new shortest path. It's going to be 12N. Get rid of that J. Moving along, the next one in line is going to be E. From E, we're unable to visit anyone else, so we just put a red box around it, and then finally we visit O, and of course O is our destination, and it's the last one we're going to visit in this case. Now, tracing this back through the network, what you can see is that because we've already calculated or we've said where we're coming from, so in this case to get to O we've come from N, you can simply track it back like this. From N we go to I. From I we're going to go to H. From H we're going to go to G. From G we go to F. And from F we're going to go up to A. So the shortest path from A to O is going to be A via F via G via H via I via N, and finally getting to O, and it's going to have a weight of 12 units. So don't say 12N, because the N, we only use that to denote where we've come from. It's going to be 12 units. So in summary, this has been a video demonstrating how we can apply Dijkstra's algorithm to calculate the shortest path between two nodes within a network. But before we leave, I'm going to show you one more thing that we can do with this. As well as being able to get the shortest path within the network, it's also going to reveal to us the shortest tree or the shortest spanning tree within a network from A. Now from A, remember we also we also looked at every other node within this network and it showed us where we came from. So to get to B, we came from A. Do this in a different color. Let's go blue. To get to B, we came from A, and to get to C, we came from B. To get to D, we came from C. And to get to E, we came from J. So down like so. To get to J, we came from M. Must be a mistake. Came from H. It's not a very clear H. To get to K, we came from F. To get to L, we came from K. To get to M, we came from H. And therefore, what you can see is that we've got the shortest spanning tree using Dijkstra's algorithm again. You'll come across this when we look at Prim's algorithm, and what you'll find is that Prim's algorithm is basically the same thing as Dijkstra's algorithm with a few less steps involved. So we'll leave it here for now.